In this video, I'm going to walk through how I measured the limiting magnitude of an image of the Great Orion Nebula using a modest amateur telescope and an iPhone. Rather than relying on estimates or rules of thumb, this approach uses real observational data and a calibrated star chart to determine how faintest star this system can actually detect. This method shown here can be applied to almost any telescope and camera combination. Here's the equipment I used to capture the image. The Celestron telescope has a focal length of 400 millimeters and a 70 millimeter objective lens, paired with a 25 millimeter eyepiece. The mount is a simple alt-az mount with no tracking. The camera is an iPhone 15 placed behind the eyepiece using a camera adapter. The image used in this analysis was taken from a 5-second exposure, which is short enough to limit star trailing while still recording faint background stars. Astronomers describe brightness using the magnitude system. This is an apparent brightness scale, meaning it describes how bright objects appear from Earth. The scale is inverted. Smaller or negative numbers indicate brighter objects, while larger numbers indicate fainter ones. It is also logarithmic, so each step in magnitude represents a constant ratio of brightness rather than a linear change. To put magnitudes into context, the Sun has an apparent magnitude of about -26, making it extraordinarily bright. The full moon is around -12. Bright stars such as Vega are near zero magnitude. Under dark skies, most people can see stars down to about magnitude 6 with the naked eye. Large space telescopes like Hubble can detect objects approaching magnitude 30, far beyond what ground-based amateur systems can reach. Limiting magnitude is the faintest star that a telescope and camera system can reliably detect under specific conditions. It depends on several factors, including aperture size, optical quality, camera sensitivity, sky brightness, and exposure time. Because these factors vary, limiting magnitude is not a fixed property of a telescope, but something that must be measured under real observing conditions. This slide shows the image of the Great Orion Nebula captured with the telescope and iPhone using a 5-second exposure. In addition to the nebula itself, numerous stars are visible across the field of view. These background stars are critical because their known magnitudes allow us to determine how faint the system can detect. To determine accurate star magnitudes, I used a calibrated comparison chart from the American Association of Variable Star Observers, or AAVSO, for the variable star BM Orionis. The chart was reversed to match the orientation of the telescope image. Each star in the chart has a precisely measured magnitude, making it a reliable reference for visual comparison. By visually comparing the stars in the Orion image with the AAVSO chart, all stars down to magnitude 11 were clearly visible. The faintest star that I could confidently identify had a magnitude of 12.3. Based on this comparison, the practical limiting magnitude of this telescope and camera setup under these observing conditions is approximately magnitude 12. This experiment demonstrates that even a relatively small telescope combined with a smartphone camera can reach surprisingly faint magnitudes. Using calibrated star charts allows the limiting magnitude to be measured directly rather than estimated. This provides a realistic understanding of what the equipment can achieve under actual sky conditions. Thanks for watching. I hope this walkthrough helps you better understand limiting magnitude and how to measure it using your own telescope and camera. Clear skies, and I'll see you in the next video.